hopefully the lighting is a bit better this time. Well, okay, so we're on part 2, and this time we're actually gonna get to solving the equation we came up with. Well, we derived in the last part. Alright, so here's the same wave thing, and then here's the equation we found, and so let's get about solving it. So first, right, we have ux of t. Now this is a bit difficult to solve, so what we're gonna do is we're gonna separate ux of t into two variables. So we have uxt, and we're gonna make it into a function of x of x multiplied by, let's say, t of t. Right. So now that we define this as that, we could plug this into the equation. So I'm skipping some rearrangement steps here, but here's how it goes. Alright, then now, once again, we're trying to separate these variables. So we're going to rearrange again. And here I'm just going to write the capital letters to represent the function instead of writing the bracket t, bracket x. So just to simplify everything. Alright, so here's our separated, well, not separated yet. Well, separated, whatever. So now we could, the only way for these two equations to equal each other is if they equal some constant. So here, I'll just write it out for you so it makes more sense. So you could split it into something like this. Oh, I guess now you don't even need the partial derivative signs, because now you just have normal, well, only one variable in the entire equation, so you will have 1 over x d squared x dx squared. Yeah, so you have these two equations. Yeah, they're a little messy. Sorry about that. Okay, so let's rewrite this into something a little more easy for us to use, let's just say. So now we'll have to these two key equations. We're gonna use dx squared minus kx equals 0, and d squared t dt squared minus k squared t equals 0. Okay, so yeah, I must try avoiding. Oh, okay. I guess the red pen is still quite visible. But anyways, here, right, is something known as a linear differential equations with constant coefficients. Okay, I'm a little close to the stand nearby, so I can't kind of scribble that. But it's linear differential equation with constant coefficients. And these are actually, well, we're able to solve them without too much difficulty. But before we do that, let's actually warm up. Well, I mean, we have to do this anyways, but okay, anyways. So, okay, let's consider the first case, right? Let's say if k equals 0 in this equation. So if k equals 0, right, then, right, these two terms become 0, and we'll just have d squared. Okay, I meant to write x first, but it is what it is. Okay, equals 0, and d squared x dx squared equals 0. Yeah, because these two terms went to 0. Okay, we have this, right? And well, we integrate this twice, right? We integrate this once, and then we'll have some constant. Say we integrate, right? just I'll integrate this once. We'll have dt equals, let's say, constant 1. So let's call that, well, let's call it a1. Okay, and the same thing for this. dx equals a2, right? And then let's integrate this again. Okay, well, let me just be a little more precise. Okay, so we do this, right? And then we'll have something that's like this. So t of t equals, oh my, yeah. Okay, I'm trying to move this a bit without falling. Okay, there we go. Equals a1x plus b1. So we have these two, right? So these two solutions, a1x plus b1, a2x plus b2. Now, if we look back into this diagram, right, we have a few restrictions. So as you can see here, right, when x equals 0, well, the function u value is 0, and also when x equals L, the function is 0. So then we have something known as the boundary condition. And that is, as I've stated earlier on, well, these two just equal. Alright, so let me just circle this as weird, as it's gonna come up quite often when we're trying to find the solution. Okay, so now, right, if we look at this, alright, sorry about the cut. I kind of lost myself there. But okay, what I was trying to say, after I recollected what I was trying to say, is okay, well, we have the boundary conditions, right? And we have these two equations. Now, the only way for this boundary condition to work, when you plug in x of 0, x of L, right? And for the function to still be equal to 0, is if, right, we look at t of t, that the a1 and b1, right? You could try for yourself, and you'll pretty much come to the same conclusion as me. a1 equals b1 must equal 0, because if you plug in L here, right, let's say even if a2 is 0, right, this will be a b2 left, right? And okay, anyways, but whatever. So in this case, right, t of t, that means that it always equals 0, or something. This always equals 0, right? Obviously, this does not describe the actual wave, right? That just means like from here to here, we just have a straight line. And there's like nothing going on. And that's what we call a trivial solution. Now, it's an actual solution, right? But then it doesn't have actual, like, any physical meaning. So we usually want to ignore these. So in conclusion, right? K equals 0, right? All the solutions are trivial, so not of physical importance. So now, let me just flip to the next page. Okay. Oh my goodness. Okay, my setup almost collapsed. Alright, so now let's talk about the other cases, right? Let's check the other two cases. So the first one now we're gonna do is K. Wait, I'm actually drunk. Right, K larger than 0. Okay, so for the case K larger than 0, now because K does not equal 0, right? Oh my, okay, the lighting is getting bad again. Okay, because K, right? Because K does not equal 0, we will end up having to solve these differential equations. And well, before we get on to solving that, right, let's actually just solve one of these equations in the general form. So let's say we have this. This is basically the form that the equations are on. Now, how do we solve this equation? Well, this part is might sound a little sketchy, but so according to well, the textbook said, according to experience, yeah, the solution to this equation is y of x equals e to the ax, where a is some constant. And well, if you don't trust the textbook, then I also found this on Math Library text, and they also just said, yeah, by experience, y of x equals e to the ax for a differential equation like this. So, you know, I guess we're just gonna trust them for it. Okay, so if that's the case, right, we could just plug in e to the ax into here, and this becomes not very hard to solve. And well, this ends up being okay, right? You take the derivative 2 times, and okay, so now we can factor these out. Okay, so we get this. Okay, so therefore, because if y of x equals 0, that's just a trivial solution. So 8 plus minus x. And so now we actually did just find the solution to this equation, right? We found 8. So to write in the general form, since there's 2 solutions, the general solution of something like that, this is the linear sum of these two with some constant multiplying the front. So it will be y of x equals c1 e to the kx plus c2 e to the negative kx. There you go. Alright, beautiful. So that's our equation for something like that in the general form. So now let's apply the same thing to the equations we had earlier. And for k larger than 0, we'll have the solutions x of x equal c1 e to the... Oh, okay, you know what? We're gonna assume k equals this. Okay, just to make things simpler, because we don't like writing square root of k nearby. It's a lot. It feels a lot better to write just to be, well, a beta in this case. Plus x of x equals that, and t of t is very similar. It's c3 e to the vt plus c4 e to the negative. Alright, so if you think about this again, right, we apply the boundary condition to this again. Since these can't, well, the e's and the x, they cannot equal 0, right? In order for one of the solutions to be 0, and for the boundary condition to be fulfilled, right? We're gonna just remind you of this. Alright, and just in case you forgot, these are the solution we found the solutions to, these two. Anyways, boundary conditions mean these have to equal 0, right? And the only way for this to fulfill it is if at least one of them, right, c1, c2 equals 0, or c3, c4 equals 0, right? And that once again means that the every single solution and this is 0, right? Like everything was 0. So once again, right, if k larger than 0, all the solutions are trivial. Right, so here we might be wondering, like, you know, this might be a waste of time because like all the solutions are becoming trivial. Well, luckily we still have one more case. So that is when k is smaller than 0. And actually, when k is smaller than 0, if you remember correctly, there is this little thing, right? Which means that we'll encounter some complex numbers. So, so let's write it like here. Right? So for once again the same general equation, I guess. Let's write it like this now. Right now, since k is smaller than 0, we're just gonna right? This, right? We change the signs minus to plus, right? Because k smaller than 0, k by x equals 0. And to solve this, well, we'll just do the same steps. So we'll get a squared plus k squared y of x equals 0. And now we see the funny thing, right? We're gonna have a complex number. So a equals plus minus I k, where yeah. Okay, so now in order to solve this, well, technically the general solution is still the same thing as before. This is c1 e to the k I x plus c2 e to the negative k I x, right? However, we don't really like writing it like this. Obviously, like we don't really like seeing complex numbers in there. So what we're gonna do, right, is we're gonna use Euler's identity. Yeah, I think that's what it's called. We're not gonna derive it here, but basically what it is this. This thing. And we're gonna use it quite a bit when you do any quantum mechanics or things like that, because there's a lot of complex numbers. Yeah. Alright. So we're gonna use this and convert this equation into. You could do the exact. Yeah. Okay. Anyways. Cosine kx plus 4 sine kx. Now, where c3 equals Now, simplify this step by a lot. There's actually quite a few steps converting from this into this. You guys could try yourself, and you'll get the same results where c1 plus c2 will be here, ic1 minus ic2 will be there. Well, I guess it's actually not that long, but anyways, you guys could do it as an exercise. But okay, we're gonna use this, right? So now we're gonna write the result when k is smaller than 0, right? The solutions are gonna be x of x equals a cosine, and same thing, right? Where k equals, right? So this plus this equals that. All right. Now, right? If you remember, we have our boundary conditions, and we need this to equal 0. Now, okay, I'll talk about the timeline later, but we need this to equal 0, and the funny thing is, right, okay, if the cosine 1 equals 0, right, if a and b equals 0, then, like, there's no point doing any of this, right? So, let's set the sign, right, because, okay, let's think about it like this, right? In the boundary condition, right, when x equals 0, this has to equal 0, right? And we know that this will usually equals 1, so that means a must equals 0. So that means this is always 0, right? So that means that b sine bx is the actual only solution left for this. So, okay, so here's our actual solution for x of x. Now, if we look at this, right, sine bl must equal 0 in order for the boundary condition to work once again, because we're trying to make this all equal, right? And if we make b 0, then we'll just get a trivial solution, right? So we get this. So we want sine to equals 0, so now, which means that, and where n is just an integer. Okay, this is the only way for it to not be trivial. So in other words, we could write it as x of x equals b sine in pi x over l. Alright, actually, this is probably the better equation to use. So let me just now we found x of x, right? And well, if you're confused about why this to this, just I don't know, think about your trigonometry a bit, and you'll figure out why. It's pretty straightforward. Now we have this for x of x. Now time for t of t. There isn't anything too special about that. This is the cosine. Okay, where this thing is, it's basically kind of like angular velocity. It just equals some constant times, well, it's the same constant as that times the frequency, and it's also equal to, and this v is velocity, by the way. This one, don't mix these two up. This one's velocity. This one is frequency. Okay, so now that we have that, right, we're gonna try to find the, let me just underline this because this is the t of t we're gonna use. Now we're gonna find the general solution, right? The general solution of everything is, this and, this, that's the general solution when k is smaller than 0. So general solution. Okay, just making it clear to everyone. Yeah, my writing is not it. Okay, now let's write it for the entire equation, right? So now, the general solution, so we gotta consider all cases, k equals 0, k smaller than 0, k larger than 0, right? Now, that is just the sum of everything. Now, because all the other ones were trivial, they're just all equal 0. So what actually matters is the actual solution, even though it's a superposition of all the solutions, when k equals 0, k larger than 0, it really is, when it comes down to it, it's actually just k smaller than 0. So we could just write uxt Alright, here we have it. And if you're wondering, f just equals dB and g equals EP. Just to condense the thing. Now, if you're wondering what uxt earlier, well now is, because earlier we wrote unxt, right? So that's actually for each number, right? Because remember, we had like equals some n value earlier on. It was sine, I believe it's n pi x over l, right? So n actually determines, right? So that's why we had that's why we had u of n, because actually u slightly changes with each n. Because sorry, my throat is dying. Alright, back from getting some water. That was strange. Actually, I don't think I was talking for that long, but whatever. As I was saying, we subbed u of n because, well, u slightly changes with each n, because n is like an integer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And I guess for each n the value will be slightly different. Okay, so so the actual u naturally will actually be the sum of all the little u's. So that'll be Okay, there you go. Here, that's the actual expression for u x of t, and that's the general solution. Now, we could write this into a different form. If we let's use a random function, right? Let's say y of x. All right, so y of x equals, let's say, c1 cosine a plus c2 sine. Now this equation actually equals a few different things. The one we're going to use is, let's say it's called b cosine. You can also do this with sine, by the way. But okay, so here's what is another way of writing this. Now, the way to prove this is pretty easy, and I'm just gonna intuitively prove it to you guys. Okay, I drew this a little over, but okay, here, let's see this. So I'm sure everybody is, well, at least I've heard of this trig identity. And now this thing, right? This is some random constant. This is a constant called, well, the phase angle, but it's a constant. And according to this, right? This, right? If this is a constant, this is a constant, and this is a constant. Yes. Now, if you put this into here, right? This is like C1, this is C2, right? It's like all constants. So basically, these two are equivalent, right? If you apply this to this, and all the constants, it could just be determined, right? Because you could just put constants together without worrying too much. The actual part that matters, all equal according to this. So basically, you could write this into this. So the more simple way, the more common way of writing u t would be this. Oh yeah, and also this constant in the front, which we denote as an now, is the amplitude. But yeah, so this is the more commonly used form of it. Alright, there you go. So let me just highlight this once again. And this is going to be our end result for today. Yeah, this is the more commonly used one, and that one is also acceptable. And notice how this part, right, is x of x, and this part is t of t, and this is just some constant, yeah, which is also happens to be the amplitude, and this is also some random constant called the phase angle.